Okay, the next speaker we're going to introduce is Dr. Patrick Favero, who is the co-owner of Martinsville Family Medicine. Dr. Favero grew up in Collinsville, Virginia, and attended and graduated from all the local schools around here. He graduated from West Virginia School of Osteopathic Medicine in 2007 and was Vice Chief of Lynchburg Family Medicine Residency Program from 2008 to 2010. Dr. Favero returned home to begin his practice with Martinsville Family Medicine in 2010 and is a member of HAY, which stands for Helping Engage Youth Community Coalition. He also serves as the athletic team physician for Magna Vista High School. Let's give him a round of applause.
All right, thank you. So I was asked to come and speak today about alcohol and adolescent brain development. And unfortunately for you guys, I was told to make this somewhat a technical speech. So I hope not to bore you. The objectives really for what we're supposed to talk about are to understand the structure and function of an adolescent brain in order to understand the current ideas on how drugs and alcohol affect the adolescent brain. So, as we all know, the human brain is the most complex organ in the body. The 3-pound mass of white and gray matter that sits inside of our skull is the center of all human activity. It allows you to drive a car, to breathe, to eat a meal, as you're doing now, and I hope you all enjoy your meal. If any questions come up during the speech, just go ahead and stop me. I'll probably lose track, but then I'll regain my my spot. But I'd rather ask you during the conversation than at the end. So, over the last several years, there's been great advances in medical technology, particularly in imaging of the brain. For instance, we have MRIs and PET scan technology, which allow us to get in-depth looks at teenager brains, adolescent brains, without exposing them to a lot of radiation. This has allowed studies to be done to perform imaging scans of brains while in use and before and after and at different ages without exposing subjects to unneeded radiation. This is an example of a PET scan. PET scan shows brain activity while a subject is actually performing thoughts. And if you look at it on the left, there's lots of bright areas that show up. These areas demonstrate activity in the brain. The one on the right is not as bright. It was maybe somebody sleeping or some other type of activity that doesn't involve as much thought. So imaging scans done before activities, during activities, and perhaps during drug or alcohol use or on a patient that has used drugs or alcohol in the past can help show the amount of brain function. This has also changed the thoughts as far as brain development goes. This slide demonstrates that between ages 5 and 20, that there's a significant change in our brain. Typically, this develops from the back to the front, and areas of dark blue demonstrate more of an adult brain. And if you look at the 5-year-old brain, there's lots of areas of yellow and red, which is the underdeveloped brain. For many years, scientists have known that the neurons for new connections during the first few years of humans' life were created. They originally thought that these neurons were the majority of the neurons that your brain ever created. As studies have gone on, as MRI and PET scanning have developed, they've allowed us to image the brain and demonstrate that throughout adolescence and childhood, teenage years, your brain continues to develop. Even to the point that there's some adult brain development that allows memory and learning even as adults. So the old adage, you can't teach an old dog new tricks, kind of goes back to the idea of, well, originally they thought the adult brain didn't really develop any further. But in fact, new memories, new thoughts, new ideas do create new pathways even in the adult brain. So to look at parts of the brain breaks down into several different areas. Particularly the brainstem, which controls basic life functions, breathing, heart rate, sleeping. It's located deep in the skull for protection. The limbic system, which we'll talk in more detail about later, is our brain's reward circuit. It links together a number of brain structures that control and regulate our ability to feel pleasure. Feeling of pleasures motivate us to repeat pleasurable activities, such as eating. Our body enjoys eating, so we want to repeat eating because it's important for life. Other types of things that can work on the limbic system are drugs and alcohol. And when they cause the limbic system to make the body feel like it enjoys these things, it makes you more likely to want to repeat them in the future. And then the cerebral cortex, which is divided into different control specific areas of the brain. Different areas process different senses, such as the process of hearing, feeling, tasting. The front part, or the frontal cortex or forebrain, is the thinking center of the brain. It powers our ability to think, plan, solve problems, make decisions. So different parts of the brain are responsible for different areas of coordination and performing activity. The frontal lobe takes care of speech, emotions, and reasoning. The cerebellum takes care of movement and balance. The hippocampus is involved in memory and learning. The temporal lobe is involved in interpretation of sounds and spoken language. And the prefrontal cortex, as I just mentioned, is involved with rational thinking, memory, and personality behavior. This becomes very obvious in patients that we see in the hospital who have had a stroke. If they have a stroke and it knocks out a specific portion of their brain, you can normally tell that. For example, somebody has a stroke on the left side of their brain, typically they end up paralyzed on the right side of their body. If somebody has a stroke that affects their prefrontal cortex, it can actually affect their mood, and they can have normal movements of all four of their limbs, but they may just be a different person the rest of their life. The prefrontal cortex is one of the brain areas still maturing during adolescence. The part of the brain that enables us to assess situations, make sound decisions, and keep our emotions and desires under control. Most of you who have teenagers in your family or are a teenager would agree that your prefrontal cortex probably doesn't work its best sometimes and still needs to be developed because you're tempted to make, sudden decisions that may not be as sound as you'd like them to be when you look back on them. This area acts as the brain's traffic cop. It coordinates processing among counterparts in the brain. It modulates emotions. And in teens, it's not yet equipped to control the emotions and make good judgments as it is in adults. This area has been studied in depth recently, and they've actually found that teenagers, when they meet a new person and they look at their facial expressions, that a teenager's mind goes back into the portion of the brain called the amygdala, which is a prehistoric portion of the brain, to get the emotion or thought from a facial expression. Whereas an adult looks at a person, and the part of their brain triggered by facial expression is actually the prefrontal cortex. So an adult can look at a facial expression and think and use sound judgment to have an idea of what that person means by their facial expression. Whereas a teenager may look at somebody, because of the prehistoric part of their brain kicking in, they use more of their gut. They get their feeling from inside of, okay, this is somebody that's going to like me or not like me, rather than using their prefrontal cortex to come up with a good thought. So, the prefrontal cortex, while the other parts of the teen brain are shouting, the prefrontal cortex is not quite ready to play referee. This can have a noticeable effect on adolescent behavior, such as difficulty holding back or controlling emotions, a preference for physical activity, a preference for high excitement activities, such as activities involving video games, sex, drugs, music. This area also causes poor planning and poor judgment, rarely thinking of negative consequences. And more risky and impulsive behavior, including experimenting with drugs and alcohol, occur because the prefrontal cortex has not yet developed. So, for normal brain development, involves proliferation of pathways. This makes the brain versatile and able to adapt to different environments. This is followed by pruning of these pathways once they're created. With experience, the unused pathways are eliminated, and the used pathways proliferate. Sustaining pathways through a process called myelination, which involves white matter surrounding nerves, allowing those nerves to move faster and create easier thoughts. Think back to about when you're a kid. There might be a certain smell that you we're involved in just certain situations. For instance, the smell of leather may remind you of horseback riding and the smell of the saddle. Or the smell of a specific person's perfume, if you smell today, will automatically bring your grandmother's image to your mind. That is a process of myelination, process of building and proliferation of pathways. Once those pathways are created, whenever that specific smell comes into your mind, that's the thought that it's going to trigger. Smell is one of the oldest pathways that was created in our bodies, and thus it creates these very strong sensations with specific smells. Pruning, which occurs in different parts of the brain at different times, also appears to allow the brain to think more efficiently. Until the prefrontal cortex has been pruned, most young teenagers don't yet have all the brain power they need to make good judgments. Researchers suspect that the excess of synapses inside of the young brain can't easily keep track of multiple thoughts, and it can't gain access to critical memories and emotions that allow grown-ups to make sound and judicial decisions. So if you imagine the adolescent brain being a spider web, and it has webs going in all directions, that is why most adolescents have very tangential thoughts and have difficulty staying focused in certain situations. Whereas an adult brain is more streamlined, and their judgment is more sound, and they're able to stay focused on certain situations much easier than an adolescent. After the pruning down phase is complete, there was a thought of a use it or lose it principle. The cells that connect in the brain that are used on a regular basis survive and flourish, where the cells that we don't use seem to dwindle and go away and be pruned. So if a teen is involved in music or sports or academics, those are the cells in the brain and the pathways that are going to proliferate. The areas that you use on a regular basis are going to continue to grow. If a teen is involved in sitting on the couch watching the Jersey Shore or the Kardashians, then that's going to be the part of the brain that proliferates and is going to help control what the rest of their life is like. So, alcohol affects various aspects of brain development. It inhibits growth of neurons and decreases myelination. Alcohol can cause death of nerve cells. As a result, alcohol has a greater effect on the developing brain of teenagers and adolescents compared to those of adults. Drugs act on the reward system of the brain and the limbic system. This area, for example, controls emotions to different situations. For example, if you have a nice puppy dog and you get up in the morning and you're all dressed and your day is nice and the sun is shining, you're on time, you've already had your coffee, and you go outside, you take your dog for a walk, and it jumps up on your legs and it gets your pants dirty. All right? If your day's going really well, it may not bother you very much. Okay? But on another day, you're running behind, you got up late, for some reason your coffee's not made, or you made it before you got in the shower and then something happened, and by the time you pick it up it's cold, and you go outside and it's raining, and the dog jumps on you and you get muddy, you're going to react to that situation totally differently than the day that's going well. This goes back to the limbic system in our brain, which helps merge all of the information which we processed in the past, memories, thoughts, and allows us to use those to control our emotions. Feel-good signals. Dopamine is the control of most of our feel-good signals, and it's the part of our body that most drugs act on. This area causes the reward system to send too many feel-good systems when we're involved in drugs and alcohol. Also, when you're eating, your body's sending dopamine. In response, the body's brain systems try to right the balance by letting through fewer dopamine receptors. As time goes on, the body needs more dopamine to get the same effect, thus developing tolerance. The effects of drugs on the brain doesn't just end when the high wears off. When a person stops taking a drug, their dopamine levels stay low for a period of time. This period of time depends on the amount of drug they've taken, the amount of time that they've been using the specific drug or alcohol, and it depends on the individual. But after using drugs or alcohol, an individual, because of dopamine, is more likely to feel flat, depressed, and not be able to enjoy pleasurable events that they would be able to enjoy otherwise until their body corrects itself. So, how the nervous system works is basically you have a neuron or a cell that is a functional unit of the nervous system. This neuron processes with areas called dendrites and receives signals through an axon that carries impulses. This picture shows two neurons which are communicating through a long axon in the middle. And as teenagers are growing, your body's creating more neurons and more axons and creating more pathways throughout teenage and adolescent years that involve the growth and development of the brain. And these different areas can be laid down depending on your daily activities, your thoughts, your emotions, through creating new axons between neurons. So, if you think about it, our minds are like a network of roads. The roads you travel frequently are going to be the roads that in your mind are the most ingrained. For example, most of us have our same path that we take to the mall every time we go. There might be 5 different ways to get there, but you're going to drive the same way every time you go. Well, that's going to be the part in your mind that stands out the most. In your brain, if you continue to do certain activities, then those activities are going to be ingrained in your mind the most, and they're going to develop the most persistent pathways as you get older. So these neurons transmit information to other neurons. Information passes from the axon of the presynaptic neuron to the dendrites of the postsynaptic neuron. In response to an electrical impulse, the neurotransmitter molecules released from the presynaptic axon terminal bind to the specific receptors from the neurotransmitter on the postsynaptic neuron. After binding to the receptor, the neurotransmitter molecules either may be taken back up by the presynaptic neuron, or they can be degraded by enzymes present in the synaptic cleft. The synapsis is the site where chemical signals pass between neurons. Neurotransmitter is released from the presynaptic neuron terminals into the extracellular space, the synaptic cleft or synaptic space. The released neurotransmitter molecules can then bind to specific receptors on the postsynaptic neuron membrane to elicit a response. Drugs of abuse share a common action. They act on the brain's reward system, the limbic system. Within that system, they all, except for perhaps LSD, share the ability to increase the levels of dopamine in the nucleus accumbens. This almost certainly accounts for the rewarding, pleasurable effects of abused drugs. The effect of the drugs is not limited to the reward pathway in the brain. Drugs can act in various regions of the brain as well to exert the effects, but their ability to alter dopamine neurotransmitters in the ventral tegmental area and the nucleus accumbens is one of the most important factors that drives continued drug use. Nicotine binds to specific receptors on the presynaptic neuron. When nicotine binds to receptors at the cell, it excites the neuron so that it fires more action potentials or electrical signals. That move towards the synapses, causing more dopamine release. When nicotine binds to nicotine receptors at the nerve terminal, as shown in the picture, the amount of dopamine released in the response to the action potential is increased, thus causing the pleasurable effects. Receptors bind only to a specific chemical shape. They're like a lock with a specific key that will open them when used. A receptor will bind only a molecule that has the right chemical shape. Molecules that do not fit in right will not bind to the receptor and will not cause a response. This is how most pharmaceuticals work. For example, the drug Chantix, which is a nicotine replacement type drug, so that way people can get off of the use of smoking, has a specific area shaped like this triangle, just like nicotine would, and the molecule attached to it has a different shape, so that way it can fit into the same receptor as nicotine would, causing your body to think that you're smoking when you're not, allowing you to try and have tobacco cessation. Addiction is a brain disease. Research shows that abuse during the teenage years negatively impacts the memory center of the brain, also known as the hippocampus. The use of drugs and alcohol may also disrupt the development of the adolescent brain in other unhealthy ways, making it harder for teens to cope in certain social situations and in the normal pressures of life. Moreover, the brain's reward circuits, the dopamine system, get thrown out of whack when under the influence. This causes a teen to feel in a funk when not using drugs or alcohol. Sometimes it can take them a long time to get out of this funk, thus causing a negative feedback system where they continue drug and alcohol use. Plasticity of the brain is the brain's ability to change and reorganize in response to certain input. Plasticity is defined as the change in anatomy of the neurons. New synapses are formed, existing synapses are strengthened, and some synapses may be eliminated. Learning is a form of plasticity. Since it leads to structural change in the brain plasticity functions both in positive and negative directions. Neurons that are stimulated to form additional synaptic connections may grow and strengthen. However, neurons or synapses that are neglected weaken over time. This has been demonstrated through studies with mice in cages. For example, the mice on the left have no toys to play with. The mice on the left, they found, developed less synaptic connections. The mice on the right have toys to play with as well as other mice. And they found that they have an enriched brain and have more synaptic connections than the mice on the left. If you take a mouse on the right out and you keep it isolated for a period of time and then look at its brain once again, you're going to find that it has less connections than it did when it lived in an enriched environment. This poses an idea in the thought of teenagers' brains. For example, if you have a teenager who likes to do things for fun, such as playing sports and enriching activities, then they're going to develop more synaptic connections and their brain is going to flourish. Whereas if you have another teenager who may not be able to be involved in those situations, then they're going to have less synaptic connections and their brain is going to be less enriched. Brains get hardwired by what we do. This argues for doing a lot as a teenager, because that is when you have the hardwiring portion of your brain occurring. Do you want to hardwire it for sports, mathematics, playing music, or do you want to hardwire it for sitting in front of the television? This hardwiring would also go along with the use of drugs and alcohol. If you use drugs and alcohol, you're more likely to hardwire your brain to use drugs and alcohol in the future. Parents can take comfort in knowing that searching for new experiences is a normal part of adolescent and teenage years. The trick is to help your kids get an outlet in a healthy environment. For some children, it may be being involved in a school play. Volunteering in a certain situation is all you need to get the outlet that you need. Whereas for others, it may be that you can do higher impact sports, wakeboarding, skydiving, or something adventurous to get that outlet. This also poses a bigger threat when it comes to lower socioeconomical situations. Because if you don't have the means or money to go participate in those activities, then you're more likely to want to get your high from doing something such as drugs or alcohol. Alcohol in the brain. This is a PET scan, once again, that shows a 15-year-old male non-drinker, which has multiple areas of his brain that are lit up with red, and I guess that's a pink color. Whereas a 15-year-old male who's a heavy drinker only has very sporadic areas of their brain that are lit up, showing that there has been definite damage done to this young individual's brain through the use of alcohol. Researchers feel they have only begun to probe the working for the adolescent brains. Their findings already offer some new ways for parents to deal with teenagers. During adolescence, many high mental skills will become automatic, such as driving. Kids who exercise their brain, in effect, by learning to marshal their thoughts, to measure their impulses, and to understand their abstract concepts, are laying the neural foundations that will serve them for the rest of their lives. In conclusion, there are many reasons that adolescents should not drink alcohol or use drugs. It's illegal, it's unsafe, More teens die from alcohol-related accidents than any other means. It's unhealthy. We protect people from brain damage from the time they're born. We put them in car seats, we make them wear seat belts, we make them use bicycle helmets. Now we know we need to protect them from alcohol as well. Any questions? Yes?
Are endorphins similar to whatever?
To dopamine?
Dopamine, yeah.
Yes.
They are?
Any other questions? Sure.
Reversibility is, if you were talking about the mice having little opportunities in one cage, is there a reversibility? Is there a point of no return?
Right. Okay, so I don't know of a specific study that's been done, but the study that this looked at basically showed that if you're in an enriched environment, you're going to develop more enrichment and more synapses to your brain. I would theorize, like I said, I don't know the study that's been done, that if you took the mouse out of B and put it in A by itself, it would definitely decline. But then if you want to once again put it back in an enriched environment, it would improve. And I think you can see that with lots of teenagers and young kids who are involved in bad situations. If they get out of a bad situation and put in a good situation, then they do improve and flourish. And I think that the study probably has been done somewhere, but I'm not aware of it.
Same thing for humans.
I would agree. That we're using mice as a correlation with human brains.
You were showing the 15-year-old heavy drinker.
Right.
Is there a reversibility with that?
With this, there's probably less reversibility. And the reason is typically when you have a significant amount of damage actually done to the brain to cause decline on a PET scan, it's probably at a point where it's going to be irreversible.
Brain cells can't be renewed.
Brain cells cannot be renewed. The alcohol that kills brain cells, those cells are gone forever.
I have a question about genetics.
Sure.
I at one point have heard that people who are genetically predisposed to be alcoholics, like say they have a father or in their family,
Right.
when they drink alcohol, there's something about the receptors or the dopamine in their brain processing alcohol differently than people who would be not genetically predisposed to that. Is that true?
I don't know of a study that's demonstrated that. But in theory, I think the idea is that children of alcoholics are more predisposed because of the same type of responses. They're going to have increased dopamine levels with the use of alcohol. But I don't know of a specific study that demonstrates that. Any other questions or comments?
I have a question.
Sure.
When you were talking about once a brain cell is dead, it's dead, the human body always amazes me that it can learn something in another place.
Right.
So if this 15-year-old person were to stop drinking and just not do it ever again, would his brain perhaps shift where the work was being done?
It could. I've seen brains do amazing things, particularly like I mentioned earlier, stroke victims. You'll see somebody after having a stroke who's very debilitated. And as time goes on, they can make significant improvement. If this individual who has done this damage to their brain through heavy drinking quit drinking, then parts of their brain that were still alive and vibrant could probably take up some of the slack for the areas that have been damaged. Okay, thank you.